from rambling for 2.5 hours. But yeah, so I'll cover a little less material today and make sure to wrap up by 1. So yeah, I think we can do a brief recap and then dive into today's new content. All right, so here we go. Thanks for your patience here. All right, so last time we discussed what I called fingerprinting, and this this is basically can be viewed as an efficient randomized algorithm. I framed it as for 2 problems: the equality problem and permutation testing. Okay, and we're gonna make use of fingerprinting again today. So I am going to briefly review these two algorithms here. But before we do that, I'll tell you what my goal is to cover today. So we'll see something called Freivald's algorithm for verifying matrix multiplication. And yeah, so that's going to use fingerprinting as well. And I think I will tell you what the short zip lemma is. And say a little bit about it, and how you can use it in Freivald's algorithm, just as a concrete example. And that might be it, given that I have a hard stop at 1 today. But if there is time, I would say a little bit about error correcting codes, and how they connect to what we've already discussed last time and today, namely these fingerprinting algorithms. And then next week, I'll plan to cover interactive proofs and arguments, like what they are, what their definitions are, and a little bit more about basic facts about polynomials. And once that's out of the way, we can actually immediately dive into really important and fascinating interactive proofs like the sum check protocol. So for sure, within possibly today and next week might be what you consider sort of preliminaries or basic material, not like the really exciting stuff. But definitely within 2 weeks or so, we're going to get to like state of the art fascinating stuff. So hang in there. Okay, so quick recap of fingerprinting. So let me recap for the fingerprinting as applied to the equality problem first. So I described this problem as you have 2 parties, Alice and Bob, who both have really long vectors. Okay. So let's say Alice's vector is called X and Bob's vector is called Y. And this boldface F here is what's called a field, which is just, I guess I had promised I would say a lot about what a field is today, but actually I might want to defer that to next week. A field is just a set of, you can think of them as numbers, but it's a set where you can take any 2 elements of the set and you can add them together, you can multiply them together, you can subtract them and divide them. Of course, you can't divide by 0, but other, any 2 field elements that are in 0, you can, so A over B is, makes sense, is defined, for any 2 field elements, so long as B is not 0. So that's what a field is, so if you just want to, if you've never seen fields before in your head, for now, feel free to just think of the real numbers or the rational numbers. And snarks will use finite fields. The reals and the rationals are infinite size fields. But yeah, basically, a field just captures things that you can add, subtract, multiply, and divide. And so, Alice's vector is just n field elements. Bob's vector is y field elements, and their goal is to determine whether x equals y if they're the same vector, right? And the challenge here is Alice doesn't know y and Bob doesn't know x. Okay, and so the trivial solution would just be for like Alice to send x to Bob, who can just then directly check, does x equal y, entry by entry. And so the goal is to do better than that, and in particular, for Alice and Bob to exchange less information. This is having Alice send n field elements to Bob, and we don't like that. Say n is way too big. We'd rather have her send only 2 field elements rather than n. Okay. So what Alice does in fingerprinting is she will interpret her input x as a degree n-1 polynomial. And there are many ways she could do that, but maybe one of the most natural is to say x is just a list of the coefficients of the polynomial. Right, so that is she'll consider the polynomial p, whose ith coefficient is the ith entry of x. Yeah, so in that way, she's just interpreting her input as a polynomial instead of as a vector. And similarly, Bob will do the same for his. So Bob interprets y as a polynomial q. Yeah, this notation, by the way, this is a sum. So this is saying the sum over all entries of Alice's vector of that entry times the polynomial's input z raised to the power I. And in the protocol, what Alice does after we do this interpretation of x as a polynomial p and y as a polynomial q is Alice just picks a random field element r. So she picks r at random from the field, and she sends to Bob r as well as her polynomial evaluated at r. Okay, and Bob will check whether q of r is the same as p of r. If so, he'll say he'll output equal, and if not, he'll output not equal. Okay, so that's the protocol. And so Alice sent only 2 field elements to Bob. She sent r and her polynomial evaluated at r. That's it. So just like a massive savings in communication compared to the trivial solution. And as I mentioned last week, in fact, the trivial solution is optimal if you don't allow any randomness. So if you insist that, Bob always output the correct answer, you can't possibly have Alice send fewer than n field elements to Bob. But here, the answer is almost always correct. So unless they get a really unlucky choice of R, they'll output the correct answer. And in exchange for that tiny probability of making the wrong decision, they reduce the communication from n all the way down to 2. And in terms of the probability they output the wrong answer, well, here it is. So if x and y are the same, then the Bob outputs equal for any choice of r. So I'll say they output equal with probability 1. Because in the protocol, what you wind up doing is with probability 1 is p and q are then the same polynomial, and if you evaluate the same polynomial at the same point, you get out the same thing, obviously. And so Bob's check will always pass, and he'll output equal if x and y are indeed equal. And if they're not equal, then p and q are different polynomials. And in that case, the probability that they happen to pick one of the very few r's at which these 2 different polynomials agree is very small. So they output equal with probability at most probability at most. I guess it would be something like n-1 over the size of the field. And so as I discussed last time, like, if this field has size like 2 to the 128 or 2 to the 256, this probability is just astronomically small. And this would actually be sufficiently low probability that you could use this protocol in cryptographic settings where, outputting the wrong answer could lead to a catastrophic security breach. And it would be, this probability is so small that basically, the catastrophe will never happen in the history of the universe or something. And so it's actually, even though this probability is not zero, it's so close to zero that it's okay for cryptographic use. So that is fingerprinting. In the book, I call this Reed-Solomon fingerprinting, which the reason for that terminology will become clear when I say a little bit about error correcting codes, which is probably going to be next week rather than this week. But basically, the term Reed-Solomon refers to univariate polynomials. So the fact that Alice and Bob in this protocol are interpreting their inputs as univariate polynomials P and Q, that's why this is, I call this Reed-Solomon fingerprinting. And again, this terminology I'll say more about when we get to error correcting codes. Okay, and then the permutation checking protocol was the same setup, but now Alice and Bob didn't want to know whether their vectors were literally the same, but they want to know whether they're the same up to reordering. So is there some permutation sigma so that for all I equals 1 to n, x sub I is y of sigma I. So that is x and y are the same vectors, except y might be a different ordering compared to x. Okay, and here the protocol was the same, except Alice interpreted her input x as a polynomial in a different way. So here, the entries of x, rather than being the coefficients of the polynomial, were the roots of the polynomial. So this here is a polynomial where each entry of x is a root of the polynomial. That is, if x1 is 7, then p of 7 will be 0. And in fact, if there are 10 entries of x equal to 7, then 7 will be a root of this polynomial with multiplicity 10, right? So again, this is just interpreting or ensuring that the entries of x are roots of p instead of coefficients. Roots are inputs where the polynomial evaluates to 0. And so Q of z would be interpreting the entries of y as the roots of Q. Okay, and the key point is that P and Q are the same polynomial if and only if x and y are permutations of each other. So if you evaluate the two polynomials at a random point, you get the same correctness properties as before, right? Like if x and y are permutations of each other, then you wind up evaluating the same two polynomials, P and Q are the same. You wind up evaluating them both at the same point. Of course, they spit out the same thing, and Bob will say, okay, they're a permutation of each other. And if they're not, if x and y are not permutations of each other, P and Q will be different polynomials. And so there will be only a very, very small number of values R at which they spit out the same thing. So the probability that Alice happens to choose one of those very few values of R, so that the two polynomials look the same at R, is very unlikely. Yeah. Okay. So that was a recap of last time. And so today, I want to talk about Freivald's algorithm, where the goal, is a little different. The formulation of the problem that the algorithm is solving is a little different. So, but before, I described the setting as a communication problem where there are two parties, Alice and Bob. Alice knows some input X, but Bob doesn't know X, and Bob knows some input Y, but Alice doesn't know Y, and they want to compute, ascertain some property of X and Y together, while exchanging as little information as possible. Freivald's algorithm is really naturally understood not in a communication setting, but in a computational setting, meaning the goal is really, there's like a verifier, and the verifier wants to run fast. Okay, so this will really be our first probabilistic proof system. Okay, so here's the setting for Freivald's algorithm. So you have some verifier V. The verifier knows, let's say, two input matrices A and B. So let's say these are both n by n matrices, and their entries come from some field F. Again, a field is just, a bunch of numbers you can add, subtract, multiply, and divide. And her goal is to compute the product matrix A times B. Okay, and for anybody who hasn't taken linear algebra in a long time, let me just remind you, or maybe never taken linear algebra at all. That's fine. Let me remind you what is this product matrix. So the product matrix is also an n by n matrix, and the ijth entry of the product is defined as follows. So it's the sum from k equals 1 to n of aik times bkj. So pictorially, you have this matrix A with n rows and n columns, and this matrix B also with n rows and n columns. And the product matrix A times B, so if you multiply these two together, you get this product matrix, and the ijth entry. So if this is row I and column J of the product, the way that's computed is by taking the dot product of row I of A and column J of B. Right. So yeah, this is going over, summing over the entries of, row I of A, so as k goes from 1 to n, this is iterating over the entries of row I of A, and this is iterating over the entries of column J of B. And you're just taking a dot product. So you're taking, the kth entry of row I of A and multiplying it by the kth entry of column J of B, and summing up the results. So, in sort of dot, inner product form, this would be the inner product of row I of A and column J of B. So I'll call that, well, this is horrible notation. Row I of A, I'm calling A sub I, and column J of B, I'm calling B sub J. Terrible notation, but let's just, this won't come up again. So yeah, we're taking the dot product. So the ijth entry of the product matrix is the dot product of this row of A and this column of B. Okay, and so in Freivald's algorithm, what's going to happen is, there's going to be an untrusted prover, who also knows A times B, and the prover is going to send to the verifier the claimed product matrix. So it's going to send a C, which is claimed to equal the product matrix A times B. Okay. Now, in a sense, that's all the prover is going to send. So this is kind of a trivial proof system where the prover, is just sending the claimed answer and nothing else. Okay. And what Freivald's algorithm does is it's a randomized algorithm, and so Freivald's algorithm, lets the verifier check whether or not C actually equals A times B as claimed by the prover, really, really quickly. Okay, so specifically, this check, um, it runs in time, about n squared. Okay, and so uh, this is actually what we call linear time. Now it might not look linear because there's an exponent of 2 here, but the point, the inputs, have size n squared. So linear time in the size of the input matrices, A and B, right? Because remember, these matrices have n rows and n columns. So actually, writing down all the entries of A, there's n squared entries. So even reading the matrices A and B is going to take the verifier n squared time, just because A and B have, size n squared, just to read them. And so you really can't hope for the verifier to run in time less than n squared. And Freivald's algorithm lets the verifier run in time, n squared up to a constant factor. So specifically, um, I think, so to get rid of the big O notation, I think specifically the verifier in Freivald's algorithm does, um, should be something like 2n squared, field multiplications, and maybe 2n squared field additions or something like that. We'll see what it is in a second. Um, so, so maybe, I'm going to do the counting, when I tell you how the algorithm works, and maybe I'll revise these constants a little bit or something. And so, yeah, throughout the whole book, and this study group, I'm going to consider, one field operation like addition or multiplication as like one time step. So one field addition or multiplication as one time step. So when I say, this algorithm runs in n squared time, what I really mean is n squared field operations. Now, when you actually, get very, very precise, it might not actually be, reasonable to consider one field operation to be one time step, right? Like, if you're working over a field of size 2 to the 256, um, like field operations in that field are certainly much slower than a field operation in like a 64 or 32-bit field, which has size only 2 to the 64 or 2 to the 32. So, it's fairly crude to just say, well, one field operation is one time step. But it's going to make it, much easier to talk about the runtime of our algorithms and of our proof system prover and verifier, if we just, pretend like one field operation is one time step, and only as needed do we dig deeper and say, well, exactly how long does a field operation really take here? Okay, so that's Freivald's algorithm. Now let me pause. So that's what it achieves. So, I'm going to. So I'm gonna before I tell you how the algorithm works, I will briefly say, why is this interesting. I sort of told you already. The verifier is running, within a constant factor of as fast as we can hope for the verifier to run. That is why this is interesting, but I'll elaborate shortly. Say a little bit more about that, and then I'll tell you how the algorithm works. But I think I've been talking like 20 minutes straight without pausing. So let me stop here and see if anyone wants to ask any questions, either about the recap of last time or about, the setup for Freivald's algorithm.
Uh, what is prover roughly? What is rough prover? How do you say it? What does it spend in complexity terms to get this matrix multiplication result?
Yeah, so great. That's a great question, and it's exactly, what I was going to, elaborate on, with this. Why is this interesting? So, yeah, the prover is just going to the honest prover will merely compute the right answer and send it to the verifier, like that. That's it, right? So, you know, uh, if the prover just happened to know the right answer somehow, it could potentially spend no time at all. There are some contexts where, the prover, would be claiming to know some piece of information, in this case, the product matrix. And it's sort of in the application, it itself determined that piece of information. And so I wouldn't actually have to spend any time computing it. Um, so that setting doesn't make too much sense in most applications of matrix multiplication, but this does come up all the time in cryptography. Like if the prover were claiming to know like the password or secret key controlling like a Bitcoin wallet or something, um, it doesn't have to like compute the password, right? It chose the password itself. So it just knows the information it's claiming to know, and it doesn't have to spend any extra work computing that information. But in this case, you're essentially asking like what is the fastest known algorithm to compute this product matrix. So if the prover didn't know the product matrix for some like um, special reason, like, and it did have to compute the product itself from scratch, how fast can that be? I assume that's what you're really asking. What is the fastest known algorithm for computing, the product matrix A times B? Okay, and the answer is certainly more than linear time. So I don't have the exact runtime in front of me, but it's something like end of the 2.378 something something something. And so I'll get, just it's not really important for snarks, but I'll give a brief history of this. So the naive algorithm that sort of directly follows from the definition of matrix multiplication here takes n cubed time. Right, because for each of the n squared entries of the product matrix, there's an inner product being computed here of size n, right? So there's n squared entries of the product matrix. Each take time n to compute in the sort of direct naive way. That's n cubed time total. So the naive algorithm is n cubed time. I believe for a brief period of time, many decades ago, people thought this was optimal. And I think Strassen was actually trying to show that the algorithm was optimal. I might be mixing this up with Karatsuba's algorithm for multiplying two large integers together. But anyway, so there was an improvement to this in the I don't know what decade. Maybe it was the 1930s or 40s, or maybe it was no, Strassen's not that old. Anyway, sometime in the 70s or earlier, between 1940 and 1970, Strassen realized you could do better, and his algorithm runs in something like end of the 2.8 or something. Um, and it's something called a divide and conquer algorithm. The details aren't that important. And this has been progressively improved. And it's an active area of research, and every few years they will manage to like slightly reduce this exponent. Um, and you typically see the improvements in like the fifth or sixth digit. If the actual exponent, I don't know what it is right now, but if it's like 2.378, I'm just making up numbers, 456. Every few years, like this six will go down to like a four or something. Something. You know, um, some tiny improvement, but like matrix multiplication is so fundamental that computer scientists, even care about a tiny improvement. And like, obviously the techniques used and the insights to get that improvement might be interesting. And anyway, to cut to the chase, it's widely believed, okay, that actually, like the right runtime is n to the 2 plus epsilon, meaning you think of this epsilon as like some very very small constant. So it's widely believed you can get really really close to n squared time, but not literally achieve n squared time. Um, what's more, like anything that's asymptotically faster than Strassen's algorithm, as far as I know, is impractical. So like Strasson's algorithm is decently practical and actually is actually used sometimes. Um, but any improvement over Strasson's, like it's an asymptotic improvement, but the hidden constants get so much worse that it's not actually worthwhile, as far as I know, to use any other algorithm besides naive matrix multiplication and or Strasson's algorithm in practice. So the point is that the verifier is sort of saving time by not computing the answer itself, right? Like if you could just compute the product matrix A times B in n squared time, there'd be no point to asking the prover to do it. The verifier could just ignore the prover and in the same amount of time compute the answer itself. But what's happening is like all known matrix multiplication algorithms take much longer than n squared time. And in fact, we think that like even in some distant future where we actually figure out exactly what is the best matrix multiplication algorithm, we think that will take more than n squared time, even if it's not all that much more. And so, by asking the untrusted prover to compute the product matrix on her behalf, and then the verifier merely has to check that the claimed answer provided by the prover is the right one, the verifier is running faster than it would if it just didn't have access to a prover at all. So apologies for the typical rambling, overly detailed, 10-minute answer to the simple question, but that hopefully is an answer. Okay. Other questions?
Hello, Professor. I had a little question that about Reed-Solomon fingerprinting. So I think
Mm-hmm.
last day it was told that why we do not want to look at this as Schwarzschild, an
Mm-hmm.
interpretation of Schwarzschild. But is there any intuition behind that when you want to do an equality check, you want to interpret the vector as coefficients of the univariate polynomial, number of variables that is equal to the dimension, and but when you want to do a permutation check, you want to interpret the vector as the roots of the same univariate polynomial. Is there a reason algebraically?
Yeah, well, so one thing I would clarify is I don't actually think like you want the entries of the vector to be the coefficients of the univariate polynomial. Actually, in Snark world, in Snark applications, you would actually want those entries to be the evaluations of the polynomial over some interpolating set. But often it's more convenient for people to interpret the vector as coefficients rather than evaluations for technical reasons we'll discuss in great detail, especially when we get to the difference between snarks that use univariate polynomials and versus ones that use multivariate ones. But so there's nothing really special about coefficients versus roots. It's what's really going on is, if you want to test a quality, you just need some way of interpreting the vector as a polynomial. So like, if you alter the vector at all, you also alter the polynomial. Right. So coefficients is one way to do it, but evaluations is another, and you could come up with yet more, right? Like what's critical is like if you change, if you take a vector x and you change it in any way, you reorder it, you change one entry, whatever, you better change the polynomial. If that's what equality means. You want to know whether x and y are literally the same vector. For permutation, you want like reordering a vector not to change the polynomial, but any other kind of change to the, but like altering an entry rather than just reordering should change the polynomial. Okay. And so, and interpreting the entries of the vector as roots. So vector entries are interpreted as roots. It just gives you exactly that property. So I don't really know, an intuition besides, like multiplication commutes or whatever. Like, A times B times C gives you the same result as B times C times A or whatever. That's all that's going on. Like permutation means I don't care about reorderings. I do care about any other changes. And so it makes sense to have a big product because, you reorder the factors of a product, it doesn't change the result. But you actually change some factors and it does. I mean, that's all I can say really. Is that somewhat helpful? Does that make sense?
Yes, sir. Understood. Thank you.
Yeah, great. And I will elaborate more on, whether or not, to what extent like coefficients versus evaluations versus other things are, actually important or not when I get to talking about error correcting codes. But based on my typical rambling, we're definitely not going to get to that today. So that'll be next week. Other questions? All right, good. So that's the setup for Freivald's algorithm. And another way to formulate Freivald's algorithm, of course, would be to not have a prover, get rid of the prover, and instead to just treat C as an input to the verifier. So you could just say, you just have some algorithm. It's really in a proof system, it would be the verifier, but you could just say it's an algorithm. The inputs are A, B, and C. And the goal is to, ascertain whether or not C is A times B. But I'm going to keep calling C the claimed answer and A times B like the real answer. Okay, and so this is how Freivald's algorithm works. The verifier will just pick a random R from the field. Okay, it will set X to be the first n powers of R. So 1 R squared up to R to the n minus 1. And it will, or, this is the algorithm. I'm going to keep calling it the verifier. And it will just check if C times X equals A times B times X. Okay. And here's the key, like this is, so I did get my constants wrong, I think. So this is a matrix vector multiplication, which unlike matrix multiplication can be done in linear time. Right. So here, like the ith entry of C times X is just the sum over the entries of X, or sorry, let's put it this way. So what is it? You sum over the ith row of C and X, so you take the dot product of the ith row of C and X. So, this is an order n time computation to compute this sum. And you have to do this once per entry of CX. And so this is n squared time, to compute CX. Again, there are n, there are n. So you have this matrix C, you have this vector X. You want to compute their product. There are n entries of the output vector, and for each of those n entries, you're taking the inner product of some row of C and n of X. So that's n squared time total. Okay, and so computing CX is one matrix vector multiplication, and you can compute A times BX by first computing B times X. So let's call that Y, and then computing A times Y. Right, so you can compute, A times BX with two matrix vector multiplications. Okay, so another way of thinking about Freivald's algorithm is it's sort of reducing the task of multiplying two matrices together, A and B, to get a product matrix, claimed to equal C, to the much easier task of multiplying, a matrix by a vector, like 3 times. So again, you are going to compute C times X and compare that to A times B times X. And again, there's some, it's sort of funny that, we just discussed how the permutation argument, permutation checking via fingerprinting exploits commutativity of multiplication. We're exploiting it here as well. So, like the verifier wants the real product matrix times X. But fortunately, in order to compute the real product matrix times X, you don't actually have to know the product matrix. You only have to know, you only have to know BX and then multiply A by that. So at no point is Freivald's algorithm actually multiplying the two matrices A times B, because it only cares about A times B times X, the vector X. Okay, so that's it. So Freivald's algorithm, the runtime is order n squared, because all it did was, you picked a random field element, you computed, the first n powers of that random field element, which you can do with just n multiplications, even less, slightly less. R times R is R squared times R is R cubed times R is R to the fourth. So to get another entry of X, you just do one more multiplication. And so there are, fewer than n multiplications needed to get X. Once you have X, you do 3 matrix vector multiplications. Each of those is like, n squared field multiplications. And so in total, that's, like something like 4n squared multiplications in total. And some number of additions also. I don't want to count them exactly, but yeah. So it's order n squared field ops in total. Okay, that's Freivald's algorithm, and then its correctness properties are closely related to the correctness of Reed-Solomon fingerprinting. And as we're about to see, in fact, Freivald's algorithm can be viewed as a literal application of Reed-Solomon fingerprinting. So here are the two facts. Okay, so one is obvious. If the claimed answer actually equals the real answer, then for any X, so for any choice of R, of course, if I multiply C by X, I get the same thing as if I multiply A times B times X, just because C and A times B are the same matrix. So if I multiply them by the same vector, I get the same result. So this, Freivald's algorithm will, if C equals A times B, Freivald's algorithm will always output equal, which is good. So the interesting situation is, what if C does not equal A times B? Okay, so then we're going to see that and I'll explain why this is true in a second. The probability that Freivald's algorithm outputs equal is just at most n minus 1 over size of the field, which was exactly the probability we saw for Reed-Solomon fingerprinting as well. Okay, and here's the proof of that. Okay, so if C does not equal A times B, then there's at least, by definition, of what equality means, right? There's at least one entry of C that does not equal the corresponding entry of A times B. So, for some entry ij, Cij does not equal A times B ij. Right. Yeah. If they're not the same matrix, they differ in at least one entry. Yeah. So note. So the ith entry of Cx is just the Reed-Solomon fingerprint at R of row I of C. And similarly, A times B times X, the ith entry, is the Reed-Solomon fingerprint of row I of A times B. Okay. That's because, remember the ith entry of Cx was just the sum over the entries of the ith row of C of Cik times xk. And remember, the kth entry of X was an appropriate power of R. Okay, so what's happening here is, we are interpreting, in this equality here, we are effectively interpreting row I of C as the coefficients of some polynomial, and evaluating that at that polynomial at R. Like that, so the ith entry of Cx, what that is the result of interpreting the ith row of C as the coefficients of a polynomial and evaluating the polynomial at R. So in other words, the ith entry of Cx is the Reed-Solomon fingerprint of row I of C. Okay. And so, if there's some entry ij in row I of C where the ijth entry of C does not equal the ijth entry of A times B, what we're doing here is we're taking two Reed-Solomon fingerprints of different vectors, right? So what this is saying here is row I of C is not equal as not the same vector as row I of A times B. And what Freivald's algorithm is doing is just doing like row by row Reed-Solomon fingerprints. And so if C does not equal A times B, just focus on a row where the ith row, focus on row I where the ith row of C is not literally the same row as the ith row of A times B. Freivald's winds up Reed-Solomon fingerprinting that row. It's just the ith entry of C times X. And so, as we explained with Reed-Solomon fingerprinting, since, if you wind up comparing the Reed-Solomon fingerprint to two different vectors, the probability the fingerprints match at R, even though the vectors themselves are not the same, is at most what I claimed up here, n minus 1 over size of field, where n is the length of the vectors. Yeah, so, that's the analysis of Freivald's algorithm. So effectively, what's going on here is it's just a row by row Reed-Solomon fingerprint, where the ith entry of C times X is the Reed-Solomon fingerprint of the ith row of C, and similarly the ith entry of A times B times X is the Reed-Solomon fingerprint of the ith row of A times B. And so if there's even one row of C that does not exactly equal entry by entry the corresponding row of A times B, these resulting vectors won't be the same vector. So that's Freivald's algorithm. Again, it's it avoids the verifier explicitly computing the product matrix A times B by observing that the verifier doesn't need to know or doesn't need to compute the product matrix itself. It merely needs to compute a row by row fingerprint of the product matrix, and it can actually get the fingerprints out in linear time without ever explicitly computing the entire product matrix. That's Freivald's algorithm. Okay, so that's our first proof system. So the verifier in this proof system is up to a constant factor as fast as you can possibly hope for it to be, because it has to at least read the input. And in particular, it's faster than if it just had no access to any prover at all. So it's somehow saving time by asking an untrusted prover to compute the answer for it, and then checking the result for correctness with an astronomically small probability that it accepts an incorrect claim as valid. Okay,
Excuse me. Yes. What would change if x, if vector x would be composed from just all random numbers and not powers of a single random number?
Yeah, great question. Thank you. Yeah, so if x were completely random values, all random field elements, okay, the probability, this n minus 1 over field size probability would fall. So life would get better. So would fall to 1 over field size. So that would actually be better in terms of failure probability. And in fact, Freivald's original algorithm Like the actual Freivald's algorithm does this. And the reason I like to set X to powers of a single field element R is just so that the Freivald's algorithm like really becomes identical to Reed-Solomon fingerprinting. Okay, and in particular, as well, you don't need the notion of multivariate polynomials to prove this statement about what the failure probability is when X is fully random. But that is sort of the cleanest and nicest way to analyze it. And so, I use powers of R in the book just so that you can analyze the error probability. If you use Reed-Solomon fingerprinting, you can analyze the error probability via facts about univariate polynomials. You don't need to talk about multivariate ones. And so I think a lot of people are more comfortable, like at the start of this study group, thinking about univariate polynomials, and so it just seems like simpler and more more comfortable to describe a variant of Freivald's algorithm that you can analyze just by talking about univariate polynomials instead of multivariate ones. But yeah, like the failure probability actually goes down. On the other hand, in practice, like in a cryptographic system, like a snark or something, right? Like these end field elements would actually, like in a snark, these end field elements would be chosen typically via the Fiat-Shamir transformation, which involves cryptographic hashing. And so actually the bottleneck for the verifier, the time bottleneck would actually likely just be generating all n random field elements via hashing. And so yes, like the failure probability, which translates to like security of the snark, goes down if you have n random field elements. But if these n random field elements really come from evaluating a hash function n times, that can actually be slow and a bottleneck. Whereas here you just pick one random field element and then derive the other n-1 entries, or n-2 or whatever of X just with field multiplications, which are actually much cheaper than hash evaluations typically. So that would be sort of a downside. Here we have n random values that in Snarkland would come from hash evaluations. Here we only have one random value, and so yes, you get a better failure probability, better security if X has n random values, but it does potentially come at some kind of price. Okay, does that make sense?
Thanks a lot. Very insightful answers, more than I more than I hoped to get. I just just to be sure, I wanted to reiterate on this. Fiat-Shamir in the sense of snark, I can understand this, and for the Freivalds, it has nothing to do with it, right? Since this randomness completely disjointed from the prover.
Yes, exactly. So if you literally were not using a snark, but like just wanted a randomized algorithm to check matrix multiplication, then you may well just really choose n random values. Yeah, these values would never be sent to the prover, and so they don't have to sort of come out of a cryptographic hash function or whatever. And so yes, you're exactly right. If you're just looking at Freivald's algorithm, this commentary on fiat Shamir just is not relevant whatsoever.
Am I correct that it is even just one step further? If we actually use Fiat Shamir here, then the prover can know this, can calculate this randomness and cheat.
Oh, well, okay. So it's a funny thing. I mean, this is like the magic of fiat Shamir. Um, so okay, so fiat Shamir is a technique to take an interactive protocol and make it non-interactive. Okay.
Yes, now I see the answer, but yes, that's
Yeah, yeah, exactly. Yeah. So for the prover in its head could try to come up with. Okay, so I guess this is I for the larger group, right? I should point out, like, if the prover knew what x would be, so it knew the entries of x um, before choosing the claimed answer C, it could easily choose a C. It could do an attack. It could choose a C so that C is not the right product matrix, but C times X equals A times B times X. Yeah. So it's really important that the prover, when determining the claimed answer C, does not know what this random vector X will be. If the prover did know what X would be, when it chooses C, it could easily choose, like, just trick the verifier, choose a C that, like, agrees with A times B at X, but nowhere else. And then so fiat Shamir is this, like, magical technique where you um, you actually make X a deterministic function of C, but because that deterministic function is defined through cryptography, it prevents this attack anyway. And so we won't talk about fiat Shamir in detail for probably, I don't know, a month or something. But it's this magical thing that would so fiat Shamir would let X actually be like a cryptographic hash of C. This is to be clear, this is a cryptographic hash like SHA or something, and still be secure. But in this, as I described this protocol today, like, the verifier chooses, today, forget about fiat Shamir. Say the verifier chooses X at random. After the prover sends C. And so, clearly the prover, doesn't know X when it selects C. All right, and this is going to come up over and over again in snarks, where we're going to, like, the prover is going to commit to data, like commit to a claimed, some claimed data, like C here, and then the verifier is sort of going to want to apply some randomized checking procedure on that data. And if the prover knew the randomness that the randomized checking procedure would use, when it chose the data that it's committing to, security of the snark would be out the window. Okay, but fortunately, we have cryptographic commitment schemes that can let the prover sort of, commit to the data and then only then learn the randomness using the randomized checking procedure, like this X here. And not go back and, like, change its mind about what the committed data is. And so you sort of get the best of both worlds, where the verifier itself doesn't have to choose the randomness to be used in the randomized checking procedure. Like, the prover can choose the randomness via fiat Shamir, and nonetheless everything's secure, and, like, the prover cannot actually kind of figure out what the challenge will be. The randomness will be to check the committed data before it actually commits to the data effectively. So anyway, I'm going to stop rambling. Hope that made some sense. I can take maybe one or two more questions, and then but this is what I wanted to get through today. So I'll declare it a success, and we'll go through error correcting codes and the short zip lemma next week. Okay, so
one question, please.
Yeah, please. One more question.
I was wondering if we could save some further computational effort here if we do not let V compute and compare the whole vector. Like, for example, I mean, I guess we always have to compute Y, so B times X. But could we then just compute and compare a random smaller number of entries and save some computational effort and get some kind of trade-off between the error probability and the computational effort?
Yeah, so great question. No, that doesn't work, and the reason is consider where C and A times B differ in just one entry. Then, like if you only check a small fraction of the entries of C times X, the chance you happen to pick the row that contains the one wrong entry is actually quite small. Okay.
Okay, but if it's not a small fraction.
Yeah, I mean, so if if you just assume that C differs in most entries from A times B, then yeah, something much simpler would and more efficient would work. But at that point, you literally just could have the verifier ignore the prover and or sorry, not ignore the prover, just directly check like one entry, compute, the verifier could just compute just one entry of A times B, for a random IJ or something, one entry IJ in it can do that in linear time. It actually can do that in order n time, right? So that's sublinear time then, and just check that entry. So.
Okay, yeah.
So that assumption kind of trivializes the problem. Yeah. Does that make sense?
Yeah, thank you.
Yeah, and what I can say, and there's actually been papers on this, like what you could do is not just pick a random X, but also pick a random X and Y, and you could compare Y times C times X to Y times A times B times X. And this is actually more time for the verifier than Freivald's algorithm, but it does have this nice property that Y times C times X is just one field element. So whereas C times X itself is n field elements, Y times C times X is just one. And similarly, Y times A times B times X is one field element. And people have looked at this. If what they really, really care about is like the space complexity of the prover, this can be interesting because the prover winds up just having to store like the one field element rather than the entire vector C times X. So there are variations, yet more variations of Freivald's that become interesting depending on exactly what costs you care about optimizing. Yeah.
Is it okay to say that in this last variation, in this last approach, we are going from the function to committing to the function?
Well, there's no cryptography here. So, but what I would say is, so C times X is like contains a Reed-Solomon fingerprint for every row of C. But then if you take C times X and you multiply that by Y, that is if Y is chosen, as powers of a single random field element, that's a Reed-Solomon fingerprint of C times X. So C times X is like a row-wise Reed-Solomon fingerprint to C, and then Y times C times X is a Reed-Solomon fingerprint of that. So this is like fingerprint the rows, and this is like fingerprint the result. Does that make sense?
And so, is it non-hiding commitment, or
So
it doesn't qualify? So.
yeah, so the issue, it's not a commitment, it's not a cryptographic commitment, and the issue is exactly what I said here. And by the way, I do have to wrap up in just one last minute here, so I'll make this the last question. But yeah, so the problem is that if the prover knows X when it chooses C, you have a problem. And so with commitments, it's so imagine you define like Y times C times X. You wanted that to be a commitment to C. Well, the problem is like the prover could take any matrix it cares about, D, right? It could commit to it as y times c times x. But at that point, it knows y and x. It knows the randomness that was used to compute, what we're calling a commitment, but it's not binding. It's not a commitment. And so then when it goes to open the commitment, it's very easy, to find, lots of matrices, like say C, D, whatever, so that y times c times x equals y times d times x. Yeah, that's the problem. This is why this can't possibly be binding. Yeah, like a binding commitment, it'd be like you need the property that finding two things that result in the same commitment value is intractable. And here we just don't have that, because once you tell me any two vectors y and x, simple linear algebra will let you find a lot of matrices that have this property. So you're going to need a crypto system like a cryptographic hash function or something to actually get a commitment. Okay, I unfortunately need to run. So thanks so much for the questions. I'll see you next week, and we'll talk about short Zipple and error correcting codes and get as quickly as we can to the SumCheck protocol and interactive proofs. Okay, and any more questions, put it in the Discord and I'll follow up later today. So thanks again. I'll see you next week. Bye.